Hello and welcome to our screencast on bond energy calculations. Just a heads up here, for this work you're going to need a calculator and you will need a calculator in your exam also in case there are calculations. So if you haven't got one, can you pause the video now and go and get yourself a calculator. Okay, we're going to start with our usual way of starting a lesson, which is a retrieval practice. So pause the video now and answer the questions and then come back when you have completed them. Okay, so let's self-assess this work. So what is an exothermic reaction? An exothermic reaction is one that releases heat into the surroundings. What is an endothermic reaction? An endothermic reaction is one that takes in heat from the surroundings. Which of the graphs below show an endothermic reaction? Well, reaction profile 2 shows an endothermic reaction. We know this because the products are at a higher energy than the reactants. Which of the graphs show an exothermic reaction? That's reaction profile 1. And we know this because the reactants are at higher energy than the products. Okay, so looking at what's going to make us successful today, we're going to look and state what is meant by a bond energy. You're going to be able to identify all the bonds that are broken and made in a chemical reaction. And you want to be able to calculate the energy change for a reaction overall. Okay, so this is a balanced symbol equation for the combustion of methane. We've got methane plus oxygen gives us carbon dioxide and 2 molecules of water. Before we can make a product with the atoms in the reactants, we need to break up all the bonds in the reactant molecules. So just like Lego, if you had two models that you'd made, before you could make any more models, you'd have to break up all the pieces into the individual pieces of Lego. And that's what we do. We break up all of these molecules into single atoms before we actually build our new products up again from the single atoms. Now, breaking a bond requires us to put energy in. For example, breaking the bond between 2 chlorine atoms, that bond there, that covalent bond, requires you to put in 242 kilojoules for every mole of chlorine. If you remember, the mole was a certain number, 6.02 times 10 to the 23 molecules of chlorine. So we have to put in 242 kilojoules if we have that number, that mole. That's what we call the bond energy of breaking the bond. And it's positive because it's endothermic. Okay, so in order to break it up from a molecule to 2 atoms, we have to put 242 kilojoules in for every mole. Okay, so building a bond releases energy. It's the opposite. So if we had 2 atoms of chlorine and we wanted to make a molecule, okay, it would give us the same amount of energy that we put in to break it, 242 kilojoules per mole. But instead of having to put it in, we get it back out again, and it is exothermic. So you notice they're both the same number, okay? But if we're breaking the bond, it's endothermic. If we're making it up, it is exothermic. Okay, so you need to get used to tables like this that you might see in your examinations. Okay, they show what we call the bond energies. So these are some of the bond energies. So if you look here, you've got the single covalent bond between a bromine and a bromine. That's 193. The single bond between carbon and bromine, that is 276, etc. Now this one here is different to that one. It's a double covalent bond, and you notice that the single covalent bond is 348. To break a double covalent bond, because you're breaking two bonds, is 612. So we don't need to add two of these together because a double covalent bond has its own bond energy. Okay, so what is the bond energy for an oxygen to oxygen double bond? Give you a couple of seconds to look it up. Yes, it's 498 kilojoules per mole. What happens in terms of energy when the bond is broken? Right, you take in 498 kilojoules of energy. It's endothermic. What happens in terms of energy when the bond is made? That's right, 498 kilojoules is released. It's exothermic. Okay, so let's have a little look at what bonds need to be broken and made during the reaction. So this is again methane and oxygen giving us water and carbon dioxide. So I want you to pause the video in a minute. I want you to tell me how many bonds need to be broken here. How many CH bonds need to be broken in methane? How many OOO bonds need to be broken in the two molecules of oxygen? Okay, so pause the video now and count. Okay, so if we look at methane, right, there are 4 CH bonds. It doesn't matter if it says HC or CH, it's still a CH bond. And there are 2 OOO bonds. Okay, so in the products, how many bonds need to be made in the C double bond O? How many of those have to be made? And how many OH or HO bonds need to be made? Pause the video now and count. Okay, right, there are 2 C double bond O bonds that need to be broken, this one and this one, and there are 4 OH bonds, 1, 2, 3, 4. Okay, right, I want you to pause the video now. I want you to define bond energy and then list the different bonds present in the molecules. So, for instance, NH, OH, CH, and say how many you've got of each. Okay, hopefully you're ready now. Right, what is the bond energy? The bond energy is the energy required to make or break a bond. So either the energy you have to put in or the energy you will get released. List the different bonds present in the molecules below. We've got 2 OH bonds or HO bonds. It doesn't matter which way round you put it. 3 NH bonds and 4 CH bonds. Okay, so that's our first success criteria. Now we're going to try and identify all the bonds that need to be broken and made in a chemical reaction. Okay, calculate the energy required to break the bonds in this molecule. So in order to do that, I'm going to go through this one with you and then we will do the ones after this. Okay, so OH, I need to look up OH, and it's here, 463. I count how many I've got of them. 1, 2. So I've got 2 times 463, and that gives me 926 kilojoules per mole that I would have to do to break those bonds. Now I want you to think about, if I was actually making a water molecule, how much energy would I release? Right, because we've got the same number of bonds and they're the same bond energy, I am going to release exactly the same amount of energy that I've just calculated I would have to break it. I would have to put in to break the bonds. So it's minus 926. The minus means I'm releasing the energy. Okay, I'm going to ask you to pause the video now, and I want you to calculate the energy required to break the bonds and make the bonds in methane. Pause the video now. Okay, hopefully you've been successful with that. So we're looking up CH bond, and the CH bond is 412. We're counting how many bonds we've got. We've got 4, so it's 4 times 412, which is 1,648 kilojoules per mole. Hopefully you got that. Okay, so what is the energy that we would release if we made a methane molecule? And if you remember from last time, it's exactly the same, only we've got a minus sign in front of it to say we're releasing the energy. Okay, again, I want you to pause the video now while we practice this. Okay, so calculate the energy required to break the bonds in the molecule. We've got C double bond O, so that is 743. We've got 2 of them, 1, 2. So we've got 2 times 743, which is 1,486. And how much energy is released when we make this molecule? Minus 1,486. Okay, again, pause the video now and calculate the energy required to break the bonds in this ethane molecule. Okay, welcome back. Right, we need to count the CH bonds, and we've got 6. 1, 2, 3, 4, 5, 6. And the CH bond is worth 412 kilojoules. So we're going to multiply 6 by 412. But we must also remember we've got a CC bond there. So we need to add that on as well. And that's 348. So 6 times 412 is 2,472. We've got 1 CC bond, which is 348. Add those two together and we get 2,820 kilojoules per mole. Okay, what is the energy released when this molecule is made? And just as the same with all the previous ones we've done, it is the same amount of energy, only we're releasing it, and we show that with a minus sign. Okay, so here's the last one. It's hard because it's got quite a lot of bonds, but this is the sort of one that you may get in your examination. So I want you to pause the video now and come back when you have calculated all the bonds and the bond energy of breaking all the bonds. Okay, right. So in order to calculate the energy required to break the bonds, we need to count them all up. And we've got 5 CH bonds. So it's 5 times 412. We've got 1 CO bond, so we're going to add on 360. We've got 1 OH bond, so we add on 463. And we have got 1 CC bond there, which is 348. So we add all of those 4 numbers together and we get 3,231 kilojoules per mole. So what is the energy released when the molecule is made? Minus 3,231 kilojoules per mole. Okay, so that's our second success criteria, being able to identify all the bonds that are broken and made in a chemical reaction. So now we're going to try and put it all together for a reaction. Okay, so there's always a balance between the energy needed to break bonds and the energy released when the new bonds are formed. And this is what decides if a reaction is endothermic or exothermic overall. If the energy released when the new bonds formed is more than the energy you're having to put in to break the bonds, you're getting more out than you're putting in, and so you have got an exothermic reaction. However, if the energy released when the new bonds formed is less than the energy that you've had to put in, you're putting more energy in than you're actually getting out, and the reaction is endothermic. Okay, so this is the energy change overall, and that is what determines whether it's exo or endothermic. The difference between the energy you're putting in and the energy you're getting back out again. Okay, so this is how we do it. We use the bond energies to calculate the energy change in chemical reactions. We will calculate the energy required to break all the bonds in the reactants. Then we're going to calculate the energy released when we are making all the products. And then the energy change overall is the energy required to break the bonds minus the energy released in making the bonds. Okay, so here's an example. So we've got our methane and oxygen making carbon dioxide and water. And here we have our bond energies. We haven't got any unnecessary ones there. We've just got the ones we're going to need. Okay, so just as we calculated before, right, in order to break the methane, we've got 4 times CH. Okay. And in order to break the oxygen, we've got 2 times O double bond O. So 2 times 498 and 4 times 412. So we've got 1,648 plus 996. So overall, to break all of those bonds, we've got 2,644 kilojoules. Now, when we're making all of these bonds, okay, we are making 2 C double bond O. So 2 times 743, 1,486, plus 4 OH bonds, 4 times 463 from the table, gives us 1,852 kilojoules. Add those together, and that will be the total released with all of it. So this is the total that we've had to break both of the reactants, and this is the total of making all of these. Now, in order to work out the energy change, we are going to take 3,338 away from 2,644, and you get minus 694 kilojoules. Now, because it's a minus number, it means that that is bigger than that. So it is an exothermic reaction. Okay, so I'm going to just give you a simpler one And I want you to pause the video now, and first of all you're going to calculate the bonds that you are breaking, then calculate the bonds you are making, and then take the second figure away from the first figure to get the energy change, and then say whether it's exo or endothermic. So pause the video now and come back when you've completed that. Okay, right, calculate the energy required to break the bonds in the reactants. So we have got an H single bond H bond, that's 436, and a Cl single bond Cl, so that is 242. So we're going to add those two together and we get 678 kilojoules per mole. Calculate the energy released in making the products. So we're looking for the H single bond Cl bond, and we're going to multiply it by 2. So 2 times 431 gives us 862 kilojoules per mole. Calculate the energy change in the reaction. So we're going to take 862 away from 678, and you get minus 184 kilojoules per mole. Now, because it is a minus number, it means that this energy is bigger than this one, so we're producing more from releasing than we're actually putting in, and it is exothermic. Okay, so this is a little bit more hard, right? I'm going to ask you to pause the video now and come back when you have completed this reaction. Okay, calculate the energy required to break the bonds in the reactants. Well, we've got a lot of bonds, so it is 8 times the CH bonds. So 8 times 412 gives us 3,296 kilojoules. We have got 2 C to C bonds, carbon to carbon bonds. So 2 times 348 gives us 696. And we've got 5 O double bond O bonds. So 5 times 498, 2,490. Add those all up and you get 6,482 kilojoules per mole. Okay, calculate the energy released in making the products. Right, well, you have got 2 C double bond O bond in carbon dioxide, but you've got 3 moles of that. So you are going to need 6 times 743, which gives us 4,458 kilojoules. You've got 2 bonds in every water, but you've got 4 of them, so you need 8 times 463, which gives you 3,704 kilojoules. Add those two together and you get 8,162 kilojoules per mole. Now, to get the energy change, you are going to take 8,162 from 6,468, and you get minus 1,680 kilojoules per mole. And because it's a minus number, you can see that this number is bigger than that number. So the energy that we've got released making the products is more than the energy we've had to put in. So it is exothermic. Okay, hopefully you've understood that. It does take some practice and you have to be really, really careful in your calculations. It helps to lay it out very clearly in your exam, okay, and do each stage at a time. If you don't understand this, have another go reading through it, running through the screencast, or seek help from your teacher. Okay, see you later. Bye bye.